All right, good morning, folks. Good to see you streaming into the Zoom room, coming onto YouTube. Excellent. Okay, so here we are. It's January 26th. Welcome back to the next Water, Wetlands, and Watersheds seminar. We are lucky enough this week to have Dr. Kathe Todd-Brown. Kathe is a good friend and colleague here in the department, so let me find where I put her bio. Here it is. Dr. Todd-Brown is a computational biogeochemist, maybe the first that you've ever met, either virtually or in person. So Dr. Todd-Brown is a computational biogeochemist who uses mathematics and computers to understand how soil breathes. She's an assistant professor here at the University of Florida in the Department of Environmental Engineering Sciences. Before arriving here, she was a postdoctoral fellow with Drs. Jennifer Baltzer and Merit Turetsky. She was also a distinguished Linus Pauling postdoc fellow at the Pacific Northwest National Lab, PNNL, and a postdoc researcher at the University of Oklahoma. She has her PhD in 2013 from the University of California, Irvine, and a Bachelor of Science from Harvey Mudd College, appropriately enough, in Claremont, California. So Dr. Todd-Brown, we're excited to hear from you today. The floor is yours. Please go ahead.
Thank you. So first off, can everyone see my screen?
No, because I stopped the share to introduce you and also to test whether we could reshare on the fly. I do that to everybody. Right. Maybe I would. There we go.
Perfect. I thought I was confused because I was in the gallery. Anyway, yeah, the pictures looked wrong. All right. So, so thank you very much for this invitation. I always love talking about sort of the connection between mathematics and biogeochemistry because it's not something that folks often think of. And I wanted to let everyone know that I'll be happy to take questions during this presentation. So what I'm going to start off with here is sort of a global overview of how biogeochemistry is represented in Earth system models and how that representation affects the projections of those models and how understanding the mathematics can help us get more out of the big Earth system simulations that are run. And then we're going to transition into talking specifically about coastal soils and sort of what are the features that are really important to understand coastal biogeochemistry that aren't in these kind of classic big Earth system model biogeochemistry representations that were designed for upland soils. So I'll talk a little bit about some modeling work that I've been doing with folks out of the Smithsonian Institute and North Carolina about modifying the MEMS and the cohort marsh equilibrium model. Yeah, so happy to take questions at any point. David, I think you're watching the chat for me. And if folks want to raise their hand, that'll also pop them to the top of my little list here. All right.
I'll pass them along.
Excellent. Okay, let's see if excellent. Okay, so why do we care about soil? Soils are a really large natural source of carbon dioxide, and there's this potential vicious feedback loop that can sort of get started under climate change. And so if we're going to understand how much CO2 is in the atmosphere, we have to understand this natural source of carbon dioxide that's being emitted from the soils. So to give you some numbers to convince you that this is really important, net primary production, which is the fixation of carbon by plants from the atmosphere into their biomass, is about 56 plus or minus 8 petagrams of carbon per year. This is balanced out by heterotrophic respiration as decomposers in the soil and litter layers eat up that plant biomass and respire it as carbon dioxide, just like you and I respire CO2, so do microbes in the soils. We have a pretty good independent estimation for the net primary production based on sort of satellite greenness indexes and sort of field surveys. It's much more difficult to get a number for an independent estimate of heterotrophic respiration, but that's okay because we can come up with this net ecosystem exchange based on budgeting exercises. We sort of know how much CO2 is being emitted by fossil fuels. We have a better feel for how much CO2 is going into the ocean. So that residual is what's attributed to your land carbon net exchange. And that's about 1 to 4 petagrams of carbon per year. So something to keep, so notice about these numbers is that that net exchange is within the error of the uncertainty for our NPP estimation. So our net exchange is 1 to 4 petagrams of carbon per year. The net ecosystem production uncertainty is about 8 petagrams of carbon per year. So what we're interested in is this net exchange, we have to do a really, really good job of estimating how heterotrophic respiration shifts as if net primary production changes. So our models have to be really good, really spot on. To put some context to these numbers, humans emit between 8 to 10 petagrams of carbon per year through the burning of fossil fuels primarily. So now we've all got ballpark numbers. All right. So what actually happens in soil? So this is a little cartoon that I had a buddy of mine draw up that represents how the microenvironment inside soils operates. So you're generally over on the right here, there's a soil core that a colleague of mine took. That's how you're maybe used to seeing soil in your garden, or if you go out and dig a hole. I like to think of soils as this little cartoon here. These brown blobs are the aggregate structures themselves. So this is mineral surfaces and other things that have stuck to it. The red and green blobs that are on these surfaces are microbes. And some of these microbes are in air voids. So that's the clear stuff over here. And some of them are in water voids, and that's the blue stuff over here. The microbes that are in the water voids are generally happier than the microbes that are hanging out in the air because they're wet, and microbes like to be wet. So oftentimes if they're not wet, then they go dormant. They can also go dormant if there's not enough food around in their environment, and that food is these little organisms, or these little cartoon chemical structures that are floating around inside of this water here. So I like to think of soil carbon dynamics as this really cool interaction between biological, chemical, and geophysical processes. Right. Models don't represent any of that. So these Earth system models are what's called first order linear ordinary differential equations. If you want the long complicated name and you remember your calculus from way back when, this essentially says that the amount of carbon that leaves the soil is directly proportional to the amount of carbon that's there. So this is sort of a classic exponential decay curve. So if you think of it as a cartoon, this is generally represented as a box and flow diagram. You have vegetation inputs coming in on the left here, going into different decay pools that are represented in the soil. So for example, dead leaves might decay faster than deeper organic carbon that's buried deep underground. So the rate of carbon that's leaving those is proportional to the amount of carbon that's there. That exit rate is affected by the environment. So warmer temperatures will result in faster exit rates. Different models will represent the connection between these carbon pools differently, and that's sort of that plus the proportion between the carbon that's there and the carbon that's leaving defines each of these individual models. If you want to think about this mathematically, this is represented by a differential equation over here on the lower left, where the change in carbon and soil carbon stocks is dc dt is equal to u of t, so that's the inputs over time, times some allocation vectors. So that's do all of your inputs go into the fast pool, or does some of it get allocated into your slower pools, minus a decay matrix, which is a diagonal matrix that represents the rate or your proportion of carbon that's leaving relative to the amount of carbon that's there, times some allocation matrix A, and this is going to be important later on in the talk, so we'll revisit this A. A says, where does that carbon that's leaving the pool go? Does it go to other pools, or is it just respired out to the environment as CO2? Times the carbon that's there. So again, this is where we get that first order concept here. Yeah, so that's the mathematics, and this is the flow diagram that represents that mathematics. So if you look at the documentation for the Earth system models that we're going to be talking about in a minute, all of them are sensitive to soil temperature and soil moisture. So those are two things to keep in mind. All right, I'm seeing something in the chat. Right, cool. Okay, so if we look at these Earth system models, what do they say? On the y-axis here is the change in soil carbon stocks over the 21st century in petagrams of carbon per year. So this is comparing the start of the 21st century, so 2000, the soil carbon average of 2000 to 2015, I believe, to the end of the 21st century, so 2085 to 2100. And I ordered, each of these bars represents a different family of Earth system models, and I ordered them based on what their modern representation of soil carbon stocks are. So over here on the left is the smallest amount of soil carbon stock, and on the right is the largest amount of soil carbon stock. Did this because when we first did this analysis, we thought that the change in carbon stock was going to be proportional or related in some way to the amount of carbon that you started with at the beginning of the 21st century. And if you think back to how that first pool model, the exit rate is proportional to the amount of carbon that's there, that might make there's some reasons to think that that might be the case. It was totally not the case. So we did not see any correlation here between the amount of carbon that you started with at the 21st century to the amount of carbon that you lost going forward over the next 100 years. So this was kind of a surprising result. And it lends itself to the question of what's going on here? Why is this happening? So in order to try to look at what was driving the differences between these Earth system models, we put it back in a black box. So each of these Earth system models had different numbers of soil carbon pools, different parameterizations for it. And we're like, okay, let's ignore all of that and let's just lump all of the decaying carbon pools together and look at what the trajectory of the NPP, so the inputs going into the soils, the soil carbon stocks, and their recorded heterotrophic respiration. And we're going to simplify the model so that we're only looking at one carbon pool. So this gives us the following equation for that heterotrophic respiration. So now instead of thinking about the change in the stock, we're just thinking about that outflux term. So that heterotrophic RH respiration there. We're going to say that that's equal to the total amount of carbon stock that's in the model. So we don't care what pool it was in, we're look at the whole thing, times some intrinsic decomposition rate. So now we've moved from that matrix notation to a scalar representation. So it's just one number. Times a temperature sensitivity function. So this function says what is the factor of increase for 10 degrees of warming. So T here is your temperature. Q10 is often 2, so you see a doubling of respiration for 10 degrees of warming. This is based on incubation experiments. And then times some, this is a generic monotonic function here. So we've got a normalized moisture term raised to a power, so that's positive. So this is a way of just representing a generic. You see more respiration at higher moisture levels. We also tried a peak function, so you would get some sort of if you were in really saturated soils, you'd see a fall off in respiration. There's some reasons to think that that might happen. This is the last time I'm going to talk about moisture here. This will come up again later on when we talk about coastal carbon. But in the Earth system models, they weren't sensitive to moisture. We couldn't pull out a moisture signal. We tried a couple of different functions and we didn't see it. So what we were able to do, and this is a very complicated graph and I'll talk through it. What we were able to do was use the temperature and the decay rate to explain the change in carbon stock across all of these models. So if we if we take that function for our heterotrophic respiration, and we assume that our inputs and our respiration are equal, so that the model is pretty close to equilibrium at both the start and the end of the 21st century, we can calculate that change in carbon stock based on the fitted decay rate at the start and the fitted decay rate at the bottom and the carbon that we started with. If we look at the correlation between the actual change in the simulations and the simplified one pool model paired with that steady state assumption, we get a really good one-to-one line. So if you're used to looking at environmental data, an R squared of 0.89 is pretty impressive. All of the modelers and the simulation folks that I talk to are less impressed by this, but my ecology friends are always really delighted with this correlation. And you're going to notice here that we've got an outlier here at the bottom. There's other reasons to believe that this model was not spun up to steady state like most of the other spin up protocols. And if we remove that, then we get a a line that's much closer to one-to-one. So most of these changes are explained by the changes in your inputs. So your NPP shifts over the 21st century and the interactive effects between your change and your decay rate. So this is why we weren't seeing that that correlation between our change in our decay rate and our initial decay rate like we were expecting when we started this study. The interactions between your inputs and your loss term, your decay rate, are really what's driving it, not where you start from. So that was a kind of a cool study to be able to demonstrate with this. So if we thought a little bit more deeply about that change in that decay rate, because we're interested in soil biogeochemistry, we can also take that one pool model and start talking about the shift in that decay rate with respect to that temperature and that moisture sensitivity parameter. There's a little bit of math that goes on here, but you rearrange the equation and you can talk about the change in the decay rate being equal to that starting decay rate times the change in your temperature normalized to 10 degrees times the log of your Q10. And again, on the x-axis here is the results from this equation for the global parameterization fits. And then on the y-axis is what we actually saw in those simulations. And again, what you're looking for is a one-to-one line with a tight R squared. And our R squared here is a little bit worse, 0.81. Still not too bad, especially considering that we still have that outlier that's not at steady state included in this analysis. With we're quite happy with this one-to-one 0.8 instead of 1 for our coefficient here. So this line fits pretty darn well. And again, this is mostly attributable to how you start your parameterization. So your initial decay rate, and then the interactive effects between that change in temperature and how sensitive your model was to that change in temperature. So this is an example of how we were able to use sort of some mathematical simplifications in our statistical analysis to tease apart what was driving the differences here in these models. All right, now this should bother you. So I just took a multi-pool model with very large changes in the order of magnitude between these pools and told you that you can simplify it with a one pool model. This should bother you. There are reasons why that complexity was added when these models were created. There were observations in generally in incubation experiments that made people think that you couldn't capture the behavior with one decay curve, that you needed to have multiple decay curves. And I just told you and showed you some pretty convincing evidence that we can capture the same dynamics and the same behavior using one model. So why? This bothered me for a couple of years. It turns out that it's because of the structure for this allocation matrix, and that understanding the mathematics of that allocation matrix combined with how we start these simulations means that that added complexity sort of collapses. So these pools, the transfer between these pools generally falls into one of three different categories. Either it's independent, so there's no crosstalk between the different carbon pools. So we call that an independent model, which is represented by a diagonal matrix, if you remember linear algebra. A cascade model, where you're moving from carbon that turns over quickly and it's getting more and more slow as time goes on. So carbon moves from those fast pools to the slow pools, but not back. So it's one direction. So we call that a cascade model, and it's represented as a lower triangular matrix. And then we've got that last model where you've got crosstalk between the fast and the slow pools. And so this is we call this a feedback matrix. And this is a full dense matrix. So you've got transfer between all of them. In all of these, carbon is not created. Although it is lost through respiration, it's not created inside of the system. And that's another key property. So if you talk to a mathematician, they're going to tell you that these are all M matrices. And one of the properties of an M matrix that falls out of the fact that you don't have any carbon being created inside of the system is that when you're at steady state and your inputs approximate your outputs, you can collapse your system. So there are two key parts in this simplification. One is that you're not creating carbon, conservation of mass. And the other one is that you're at steady state. And that second one is the difference between why these models were created using the incubation experiments, where you have no input term, you've removed your input and you're just looking at that loss rate. If you create a model just looking at those loss rates, and then you apply it to a situation where your inputs are approximately in balance with your outputs, like most mature soils, you no longer need that added complexity. You can instead reparameterize your model using just one pool and get the same behavior out of it. And that's what we were seeing in these Earth system simulations. So, oh, hey, David, you dropped a question in the chat. So does this mean the uncertainty in the parameterization outweighs any observed environmental changes? I wouldn't say it outweighs it, but it's at least as important.
That was referring to the significance of the parameter terms in the previous slide.
So here. Yeah, so if you look at...
And particularly the next one where del change in T is non-significant, but the starting K is, then the decomposition, of course, I may just not understand any of this, but that the change in the decomposition rate, the intrinsic decomposition rate, which you're interested in, does it change because climate's warming, yada, yada. The change in temperature, not so much driving it, at least over the range of observed changes of temperature, but the starting K across different models or different parameter sets, definitely important.
Yeah, so that starting K is really, really important. We've got over half of that R squared explained by that starting K. And the interaction terms. So it's not that the temperature is unimportant, it's that the temperature by itself is not explanatory. It has to be combined with how the model was parameterized. Okay. All right.
And if you want more questions, I got one more here. You just said the whole thing can be, it's so the next one about the M matrices, I have no idea about. But if the assumption is steady state, how does it, if we're looking at change in carbon stocks and pools over time, what does steady state mean here to you? That's just a bit confusing. And we can wait till the end if you want, or please.
Yeah, no, so to throw another math term at you, this is a non-autonomous system. So that means that the inputs change over time. So steady state really isn't the right term here because your inputs are not constant. So it's not necessarily that it's at steady state, so dc dt equals 0. It's that your inputs are approximately equal to your outputs. So that's a subtle difference with an important impact from a biogeochemical standpoint.
All right, thank you.
All right. Okay, so main takeaway from this analysis is that the simulation diversity, so that these really large diverse results that we were seeing from our forward difference model, is primarily driven by parameterization. There's a little bit of a component of, okay, how much warming do each of these simulations see? But for the most part, their biogeochemistry is driven by their parameters and not by which particular model they were running, the model structure itself. So that was kind of an interesting result. All right, so we can do one more thing that's super interesting using these simplifications, and one is to reuse the outputs from these models. So we can ask different questions that the simulations maybe weren't designed to run. And I'm going to give you two examples here, and they're going to come at you pretty quickly. I can answer questions on them later on if you're interested. One was to talk about what happens if plant productivity, that NPP number, was limited by stoichiometry. So the ratio between the carbon, nitrogen, and phosphorus. So what if the growth rate of these plants was limited by how much nutrients they had access to? The next question was talking about that parameter that was so important in governing our carbon stock, that Q10, that temperature sensitivity. What if there was a range of reasonable temperature sensitivities and we didn't know which one was right? How would that affect what the models projected was going to happen over the 21st century? So to do this, we did a couple of things. We started off with the inputs that were generated by the Earth system model, sort of represented by this little Earth diagram. We then reduced them by our available nutrients, and we're going to talk about how that was calculated a little bit later on. And then we drove the carbon, vegetation carbon, with that NPP. We then took the turnover from the Earth system models and calculated how much of that vegetation pool was lost to your soil carbon pool. And then we took the decay rate from those soil carbon pools and calculated what their loss term was. Where we introduced new terms here was this nitrogen and phosphorus, because these models didn't have nitrogen and phosphorus in them initially. We used observed ratios between the carbon to nitrogen and phosphorus pools to calculate a vegetation nitrogen and phosphorus pool. Ditto for the soil. And then we calculated this available nitrogen and phosphorus pool that we used to constrain our NPP fixation rate, using the turnover times from the vegetation carbon and the respiration from our soil to calculate this sort of available nutrient pool. And then we added a little bit to it to top it off with kind of annual estimates for nitrogen deposition, things along those lines that were maybe anthropogenically driven. So lots of guesses and rules of thumbs here that went into calculating this available nutrients that we could project to constrain our carbon fixation. So if we do this, we see a reduction in our NPP. Again, none of these models, well, there was one model that had nitrogen in it, and that reassuringly didn't change when we introduced this constraint. So that gave us a little bit of confidence in our simulation. But in general, the change in the net primary production, which is this top panel here, so that's the fixation rate of your plants, reduced significantly when you added a nitrogen limitation. So we're going from the gray bands to the pink bands, and then it reduced further when you included a phosphorus limitation. So going from the pink to the blue. And then if you propagated this out and calculated the change in the land carbon stock, we went from many of these models being causing increases in our land carbon, so being a sink for atmospheric CO2, to suddenly being a source for CO2. So we only had a couple of models that were hanging out above that zero line after we introduced our nitrogen and then our phosphorus limitation there. So this is a study this is a question that these simulations were not necessarily designed for, but because we understood the mathematics, we were able to ask to reuse the simulation output in new ways and get more bang for our buck. So we did something similar for modifying the respiration rate. Now this we held the NPP constant, so we weren't playing with the nutrient limitations here. But if we took a set of field trials where they warmed the soil and then we calculated the temperature sensitivity from the shifts in the soil carbon stock. There's a whole lot in that if you're a field scientist, and I'd be delighted to talk with you about that after the lecture if you're interested. We then fed it back in to correct those model outputs and recalculated what the change in the carbon stock over the 21st century would be. Here, the original is in white. If we reduced our NPP down to the lower bound of 1.6, so we have 160% of your decay rate for 10 degrees of warming. All of the simulations gain carbon, so this is lower than what their documented parameterization is. So we would expect them to gain carbon, or for their carbon losses to be smaller. And in fact, it tips all of the models over that zero line, so they're now all sinks for atmospheric CO2. And then if we go with the upper bound here, which is a 2.7, so a 270% increase in decay rate for 10 degrees of warming, we see some of the models are still gaining carbon. So some of them are still saying that soils are going to be a sink for CO2, but a lot of them are now saying, no, it's going to be a source. And some of them are saying it's going to be quite a strong source of accumulated CO2 by the end of the century. This median number, 2.2, is sort of the median estimate for that parameter. And this is quite close to the documented number of 2 that most of these models use. And so there's only a small shift in our soil carbon losses. So again, this is another example of how we can use our understanding of the mathematics to modify the simulation output to ask new questions. All right, so yeah, so if you understand the mathematics in these models, you can take these complex simulations and approximate them, understand what's driving the differences in the simulations, and then use these approximations to reuse the simulations to address new questions. Unfortunately, a lot of these answers are saying that soils may not save us from climate change. That between the parameter uncertainties and sort of what's driving our understanding of our behavior of soils and the global context, yeah, I don't know if I would necessarily bet on these personally. So it's a little bit of a sad story from a climate change perspective, but supports the narrative that really what we need to do is reduce our emissions, CO2 emissions, in order to mitigate and address the challenges for climate change. Okay, I've got what, 10 minutes left? Something like that?
I say 12 minutes if you want 5 for questions.
12 minutes, okay. In the next 12 minutes, this next part is going to be a little bit more speculative. So these models were designed for upland soils. Coastal soils are different. So let's think a little bit about what those differences are, how we capture them in mathematics, and then maybe how we can use those mathematics to look at data. Acknowledgement slides. Lots of people played into this study. The data sets for data sets, simulation results, meta-analyses, a whole bunch of folks. This is not a single person effort. All right, so coastal carbon. How is mud different than dirt? The risk of making all the biogeochemists in the room angry. Mud in this definition is a water saturated soil, and dirt in this definition is an upland soil. So, right, we're going to be talking about the coastal marsh equilibrium model. So this is work that a number of undergrads in my lab have been working on for the past couple of years, specifically Urmi, Jessica, and Farah. And this was done in coordination with the Coastal Carbon Research Coordination Network led by Jim Holmquist, with a lot of collaboration from Jim Morris and Megan Vasson. All right, so this model was designed to look at accretion rates as opposed to biogeochemistry. The biogeochemistry just happens to be important because fluffy soils are taller, basically. So when these models were designed to address the question of, will marshes keep up with sea level rise? So you have deposition of minerals at the surface of your soils, and your biogeochemistry is determining what the volume of your deeper core soils are. And so the result of those two interactions says whether your marsh platform is going to drown or keep up with sea level rise. Right, so what makes coastal soils different? So this is probably, water is, of course, the key factor here. So you've got periodic saturation of your soils. You also have different redox dynamics. So your saturated soils are often oxygen limited. And so sometimes that means that they produce methane, but not always. If they have other elements like some nitrogen or sulfur elements, will sort of shortcut that methane production, and you'll still respire CO2, but it'll be at a much slower rate because it's a more inefficient process if you don't have access to oxygen. So redox dynamics start becoming important in these models. And then you have that relatively fast, from a soils perspective, sedimentation rate that's happening at the top of your system. So if we think about that first order pool model that we were talking about earlier, and can we think about this in maybe more of an explicit saturation and sedimentation context? So this is a soil core here, and we're breaking it out by age cohort. An age cohort in this definition is 1 year of sediment deposition at the surface of the soil. So you can think of them as tree rings. So as they're buried, you get a different cohort. As your mineral cohort is buried down your soil column, your roots turn over and add the fluffy organic carbon to your system. So that introduces these fast and slow organic matter pools until you fall out of your root zone because you've been buried so much. Your root mass typically likes being up at the surface by its plants because it's attached to a stem. And so at some point, your cohorts are no longer in your root zone and they're just losing CO2. There's no inputs coming into it. So your CO2 is respired from your fast and your slow pools. Your mineral pool is just what it is. This allows us to think about the biogeochemistry in this sort of sedimentation context. So if you do this and you run the model with this depth awareness, you can get some sort of cool curves coming out. So some of these, what you're going to notice here, let's take a step back. So what this represents here is the density, so the mass per volume of the 4 main pools in this model: the fast carbon, the mineral, the slow carbon, and your root carbon. Your roots in this simulation are just a linear fall off. So you start at some maximum point at the top of your soil column and you fall down. In this case, the root zone was parameterized to be at 30 centimeters. Your fast carbon pool starts out fairly low, and then it accumulates carbon from those root zones, and then there's a tipping point where it starts losing carbon again because the inputs are slower than the outputs. So that gives us this nice little lens here. Your mineral pool here reduces as you get more carbon in your system. And then at some point, the amount of carbon is small enough that you start becoming more and more dense. So this reduction in your mineral density reflects the fluffiness in your fast pool. Unlike your fast pool in this model, your slow pool does not decompose. So this is an inert or very recalcitrant pool. So you're just seeing an accumulation of carbon in this slow pool, in this curve here in the lower right. So those are all of these are the simulation results. And if you start thinking about what are where we're at right now with this project is what are the data features that we want to tune this model to. So right now these parameters are very much, it should be about this. We think the turnover time for soil is about 15 years, more or less. And it would be really nice to tie that to some actual data points at specific marshes. So thinking about what the features of this model are that we want to be represented in our data collection, we can come up with 3 or 4 sort of key features here. The first one is this lens of the fast carbon pool. So where in the soil column is the maximum carbon density? And how does that, can we use that to constrain the turnover times for the fast and the slow pools there? The next one is this deep carbon concentration. So after you get past this root zone and your fast pools had a chance to blow off, you get this stability, this convergent stability in the slow pool. Can we use that convergence to constrain the inputs and the allocations in the root zone? So that's the second data point that we're interested in tuning towards. And then finally, the last one is the mineral concentration. So that sedimentation rate, which of course is not constant, and that's one of the complicating factors here. But can that deep mineral concentration be used to constrain our sedimentation rate for the particular marshland? So all of that to say is the next steps for this model is going to be model data integration. So thinking about depth and age. I didn't talk about depth for age here. I sort of glossed over that. We talked about age cohorts, and then I showed you a depth axis on the x-axis. That was actually one of the really interesting mathematical developments that we contributed to this study, was thinking about how to translate from that mathematically from the age cohort into a depth explicit function. Thinking about tying in the slow carbon density and the mineral density below the root zones, and how does that inform the parameterizations for the models. And then of course, tying it back into the marsh accretion under sea level rise. We've got some scenarios that we want to forecast. So simple, right? Stuff that we're going to be working on in the next couple of semesters. So at that point, I'm actually going to stop here. I could go on, but I think this gives us some stuff to talk about. If you're interested in this project, I am looking for a graduate student. And this is one of the sort of related topics that would be there.
Great, thanks, Kathe. Let's give Dr. Todd-Brown a round of applause, real or virtual, however you like. And we'll take questions from the Zoom room while the YouTube catches up for a second. So if you have a question, please go ahead and you can unmute and you can ask Dr. Todd-Brown directly.
I've got a question if nobody else. Kathe, great presentation. I always don't understand the math, but love to see somebody that does understand the math behind all of these biogeochemical processes. I wanted just the clarification and take-home message of the role that the nutrients are playing in this sort of a mass balance or net sink or source of carbon. And I guess I was a little confused as to which way does it go depending on the reduction. And then also, I guess, regardless of the outcome of that answer, how much did you credit the anthropogenic inputs of the nutrients to drive some of that? So, yeah.
Okay, so for this study, We assumed that the Earth system models were limited. We sort of took a co-limitation approach here. So we assumed that the Earth system models represented limitations in moisture, temperature, and in solar radiation, so sunlight. And then we took our available nutrients and we said, okay, given the ratio between carbon and nitrogen, or carbon, nitrogen, and phosphorus, how much carbon fixation does that support? And then we reduced the NPP for that year based on that annual available nitrogen phosphorus pool. So in all of these cases, there was no way to have a higher NPP than what the simulation was showing. But there was a way to not lower your NPP. If you had the available nitrogen phosphorus, then you could support the NPP for that year and you carried forward to the next year. So that's how it tied in to support the NPP. We then used that to scale the one pool model for the vegetation and the soil pools based on the loss ratios there. So the decay rate wasn't sensitive to your nitrogen at all, which is one, of course, an assumption in this study that's fairly glaring. There were a lot of rough guesses in this particular one. Your next question was about anthropogenic drivers for nitrogen and phosphorus.
Well, or just of that baseline condition of nutrient availability driving NPP, what fraction did you credit to anthropogenic inputs versus what might be natural atmospheric deposition, that sort of thing?
So we did not include any natural deposition that was not turnover from your established pools. So the only natural sources of carbon here, of nitrogen and phosphorus here, was either coming from your vegetation pool or your soil carbon pool. And that was dependent on how much carbon was leaving the associated pools. So we certainly got a reply in this study that said that our assumptions for the nitrogen loading were too low, and that there was more NPP fixation that was being supported than we were showing in our study here. But yeah, so one of the things that you'll notice here is that there's a strong cumulative effect. So that we assumed that at the beginning of the historic run, so this is 1850, that you had enough nitrogen and phosphorus to support your level of NPP production. And then we layered on top of that an estimation for anthropogenic inputs.
All right.
Does that answer the question?
Yeah, no, you got it. I might have others, but I'll follow up with them later. So thanks.
All right, and we have a question from Dr. Ewell. Kathe, please go ahead. Oh, you're muted. Still muted.
I enjoyed the presentation very much. Thank you for that. I was wondering, in the model where you showed the different layers going down, did you account for compression in those layers?
We did not. That would be really cool to do, though. So you could imagine how you would introduce that, maybe by making the organic matter more dense as you were moving down core. That was not included in this model. Something else that we've thought about doing is including a methane emission term or a methane allocation term that increased as you went down core, and corresponded to a decrease in your decay rate. So there's sort of some, from a biogeochemical perspective, some low-hanging fruit that we could do to play with this model to see what those effects were in the marsh platform.
Thank you.
But yeah, that would be fun to do.
So Kathe, I love that you could simplify a 2-layer model to one, and it does better or does as well, whatever. But for a lot of everything from like the plot scale to regional scale, folks who have done soil carbon storages have added a 3rd layer even, so like fast, slow, and recalcitrant, or something, even in any sort of crop model or soil carbon model. And again, with the whole matrix thing, I don't want to get into that, but is one possibility simply, thinking about the scale over which you're seeking to test these models, like at the global scale, that the resolution is sort of just comes out in the wash, whereas if you go out into the lawn right outside your window, a 2-layer model would work better? Can you comment on scale?
So I think that one of the things that you're confusing here, and it's a legitimate confusion, is that these pools here correspond to a depth or a horizon. They don't. So when people have gone out and tried to measure the fast pool or measure the slow pool, we have this sort of conceptual framing that a fast pool is like our leaves that are decaying and our slow pool is the mineral bound carbon or something. But if you try to measure that and then correlate those measurements to incubations or to observed changes in carbon stock, it doesn't match. So these are conceptual pools and not actual physiochemical carbon that you can isolate and quantify differently.
Yeah, and the models I'm thinking of, they all exist as boxes or some shape, and they're separated and they have arrows between them, just like this. So yeah.
Yes, and so it's really easy to think of these as like physical soil layers, especially if you're used to like going out in soil pits and you see, hey, there's a layer here and it's darker and it's more carbon rich, and there's a layer below it and it's lighter and it's less carbon rich. But these are all conceptual models that are defined based on when their carbon is released in a time course.
All right, well, I think we're going to have to end it there. I would like to say for everyone, one more round of applause for Dr. Todd-Brown. Thank you very much for joining us today. And for the students and everyone else watching, next week we have Dr. Chris Kraft from Indiana University. He's actually going to he's visiting UF, so he will be giving his talk in 101 Phelps in the conference room at the Center for Wetlands. Everyone is invited to attend. We'll have masks on and we will have the windows open. You are, of course, welcome to watch it virtually as well. Other than that, stay safe, take care of each other, take care of yourselves, and we will see you next week. Thanks, Cassie. Thanks, everyone.